integration, right? And in this video I will try to cover the topics as a complex integration, means contour integrals, and Cauchy theorem, Cauchy's integral formula, right? So let's start with the complex integration or contour integral. So here we will be dealing with the integrals in complex plane, where complex plane is of course having two variables, as we have the complex variable. If we talk about like z is equal to x plus iota y, and if we have any function which is depending upon this complex variable and we need to integrate this w with respect to z, then that z will be depending upon further x and y, right? So we have to deal with the two variables for such integrals, right? So let's understand how we are going to deal. Of course, we are going to integrate this function of complex variable along any path C, right? So that path C should be simply connected domain or simply connected region. What is the meaning of simply connected region? That region or that curve or that path which never intersect its branch itself. So that is known as simply connected region or simply connected domain. In fourth module we have already studied about this. So let's define the line integral in complex plane. We all know that in real integration we write our integral in single integration with respect to a single variable. But here in complex plane we have a variable z that is depending upon two variables x and y. So we need to further simplify it in terms of x and y. Then we'll apply the limits accordingly, right? Let's see what is the equivalence between complex and real line integrals. In real line integrals, we deal with the variables one at a time if we are dealing with the single integral like this. So if we have for f of x here dx, then the limits are here of x, right? Or if we write the integral in terms of y, for example, it is f1 y and dy is here. So here the limits of y are applied. But here single integral is having two variables, right? So how to deal with the two variables? This we have to understand. Okay. So here function of x and y, which are u and v, both are substituted, and dz, of course, if z is x plus iota y, then dz becomes dx plus iota dy, right? So accordingly we have substituted here the value of fz in terms of u and v, which are nothing but the functions of x and y, and dz is substituted in terms of dx and dy. So according to the variables we will be substituting the limits, right? And of course the integration is being taken over some closed contour C or simply connected domain. So this is our result after collecting the terms. This is our real integral, means real part of the integration, and this is imaginary part of the integration. Okay, so let's understand this with the help of one example. Yeah, we can also say this complex line integral is equivalent to two real line integrals on C, because we are dealing with x and y, two x's altogether. So here one example, we can see that integral along C 1 by z dz. So 1 by z is a function of complex variable where x is a cos theta and y is a sin theta. So of course if we add the two, x square plus y square, we are going to have x square plus y square is equal to a square, right? Okay, and the limits of theta are given as 0 to pi. That means upper half portion is our C. Okay, so that is closed contour C. Here you can notice this thing, right? So theta is varying from here to here, of course 0 to pi, And if we talk about the limit of x, that is varying from a to minus a, right? So before we substitute these values in the form of u, v, dx, dy, we should solve our function 1 by z in terms of x and y. So here I have rationalized the function. Here x plus iota y, either we can rationalize or we can multiply divide by x minus iota y. Both the operations will give us the same value. So same result we have obtained here, and that is x by a square is the real part plus iota minus y by a square. So here the real part of fz, it is x by a square, and imaginary part is minus y by a square. Now we will be substituting here the values. Right, so I1 is what? Integral with respect to x, because dx is mentioned here. So here the limits of x are taken as a to minus a. Right. Next integral I2 is taken with respect to y, and you can notice that limits are written as 0 to 0. So 0 to 0, we will be breaking this integral into two parts, as from 0 to a means once we have covered the path like this, upward direction, and then simultaneously for downward direction. So that's why this becomes 0 to 0, and it will be written like this, 0 to a and a to 0. So we will be solving by breaking the single integral I2 in terms of two integration. Okay, let's have a look at the solution. So line integral, okay, this question is to be continued. So first integral I1 is a to minus a. So here we have substituted the values. Of course, y is to be substituted in terms of x. So that's why here this yx is substituted in terms of x using the relation which I have shown you in the previous slide. That was x square equation of the circle. X square plus y square is equal to a square. Right, so from here we can substitute the value of y. Okay, then we have simplified it, and then after calculating we are getting this iota pi by 2. Right, this pi minus pi by 2 and minus pi by 2 gives me minus pi, and minus becomes plus, and this 2 is here. So that means this is the result of first integral. Right, so let's have a look at the second integral. The second integral is written like this, 0 to a and 0 a to 0. That's I've already told you, because y has no other path, right? It is moving from origin to this end, and then this end to here. This end is also a, right? So that's why we have taken here, and then further we'll simplify it after substituting x in terms of y. So from using the same equation of circle, we have substituted here the values of x in terms of y, right? So we can integrate it in a very easy manner, and so we are getting the result as iota pi by 2 of the second integral. Right, now compiling the result, we are getting iota pi. So in this way we can solve the complex line integral by breaking it in terms of ub dx dy. Further, ub will be written in terms of x and y, and since we are dealing with single integral, so we will convert one in terms of another, right? So in this way we can have this iota is equal to iota I is equal to iota pi, right? So by symmetry we can solve the same question for the complete circle C. If we take is here as well. So by symmetry, since it is symmetrical, so the result becomes 2 pi iota, right? In such manner. Okay, right. Now let's have another question. Integral, closed integral over C, where C is of course a circle. 0 to pi, 0 to 2 pi is the limit given. So that's why we can say that it's a closed circle z raised to the power n dz. Now I will solve this question in terms of theta. So two ways you can check, and whatever suits you, whatever is easier for you, you can adopt it, right? So here theta varies from 0 to 2 pi, and we have converted the single integral in terms of theta. Okay, so z is written as r e raised to the power iota theta. How come? Because this is what the equation of the circle, right? Equation of circle. So we can write this as mod z is equal to small r. Suppose r is the radius here I have mentioned. So if I remove this mod from left hand side, so I would write this as e raised to the power iota theta into small r, right? So remember this thing. Always the equation of a circle is mod z is equal to r. Center is at origin, right? So dz becomes r iota e raised to the power iota theta d theta. Right, so accordingly we will substitute the values in the integral. So here as well we have substituted z as r e raised to the power iota theta, and r n r this dz is substituted here, and theta is taken as 0 to 2 pi. Alright, so further we have just collected the total power of r, that's why it is here, and e raised power iota theta into n plus 1. Then it will be further integrated for, of course, n not equal to minus 1. We are getting this result. So in this way we can solve the single integral of complex variable function with respect to theta. So here once again I want to recall the property of analytic function as we are going to move towards Cauchy's theorem. So analytic function are what? Analyticity of a function of complex variable is nothing but its derivative must exist, right? Cauchy-Riemann equations, Cauchy-Riemann conditions, those are of course being taught to you. So those are nothing but ux is equal to vy and uy is equal to minus vx. Right, these conditions should be satisfied. Existence of all the derivatives of all the orders. Path independence means any path we are following to integrate the curve, that should be same, means integral should be independent of the path, right? And of course then Cauchy theorem says that closed integral over c f z dz becomes 0. Let's understand Cauchy theorem in detail, right? So if we have a simply connected region, I've already told you in the first slide, in the previous slide, that a curve, a path is such that it is never intersecting any branch of itself, right? A simply connected region means that there are no holes in the region. Any closed path can be shrunk down to a zero size. Means if we shrink this curve, it can be reduced to a single point, right? So that is known as simply connected region. Means no branches or no branch of this curve is intersecting or overlapping each other, right? So Cauchy theorem statement is if a function fz is analytic in a region R, then in closed integral over the c fz dz is 0, right? Now let's have the derivation of Cauchy's theorem. So we have a simply connected region C, and the C is defined in the region R, and we have to integrate any function fz over this region along this curve C. So that is fz is equal to w or u plus iota v. Then we can write closed integral over C fz dz is equal to this. We have already simplified the line integral in terms of ub and dx dy. Alright, so we wish to prove it with the help of Stokes theorem. So that's why here we have taken two vectors a and b as ux minus vy and this. Right, so here we have taken dz accordingly, and then using Stokes theorem we can simplify its curl here and z dot del cross b using CR conditions, and z is what? Depending upon x and y both. So using Stokes theorem and applying CR condition, we can say that this integral, closed integral over c fz dz becomes 0, right? Because we already know that CR equations are what? Ux is equal to Vy and Vx is equal to minus Uy. So this will get cancelled and we'll get 0 here, right? So that's why with respect to A and with respect to B, both are giving us 0, applying these CR conditions, right? So in this way we can derive Cauchy theorem using Stokes theorem, which we had completed in first semester. Okay, so remember the statement of Cauchy's theorem. If a function fz is analytic in a simply connected region R over a closed curve C, closed integral over a closed curve C, fz dz becomes 0, right? And it is of course path independent. So as long as the function is analytic in the region enclosed by the paths, so we can say that whatever path we follow, if we give this as A, this is point A, this is point B, and points remain same here. If we move from A to B and A to B following these two curves C1 and C2, and then B to A and B to A following these curve in this manner in a closed curve C, then integration is going to be same, right? So that is known as path independence. Already we have covered this topic in our fourth module, so we don't need to go into very much detail. This I have told you in module 4 already, so you all are aware about this. Means integral along any curve which is going from one point to another point following any path, integrals are equal, means values are same. Extension of Cauchy's theorem to multiply connected region. So we can write like this. On the previous slide, I have already told you that integral along C1 is equal to integral along C2. How come this we are going to derive it? If we have a function fz which is analytic in the region R is what? This all white portion part is region R, and closed curve C is consisting of C1 and C2, fz dz. So let's assume that it is not equal to 0, right? So what we are going to do, we are going to reach from one point to another point in this simply connected region. So we have separated it here, right? Okay, which is known as bridge to make this R into a simply connected region. So what we are going to do, we can write the closed integral as C1, which is in anticlockwise direction, is taken as positive. C1 minus C2. C1 then minus C2, and these straight lines are what? Opposite and equal. And the direction is opposite. So that is taken here as tunnel. So these two integrals gets cancelled and we are left with the two integrals C1 and C2. Why the negative sign is applied here? Because the direction of one curve is opposite to another, right? So this integral has to be 0 if we apply Cauchy theorem here. So this will give us the result that integral along C1 fz dz is equal to integral along C2 fz dz. So similarly we can switch for so many multiply connected regions. So here two curves C1 and C2 were taken, so this was equal to these integrals were equal to each other. So if we go for more loops like this, if we have this circle and inside this circle so many circles I draw, so and these are C1, C2 and so on, Cn like this. So using Cauchy theorem we can write that integral along C, which is outer curve which is consisting of all these curves, n curves, c1, c2, c3, cn. This is c. So integral along c fz dz will be equal to integral along c1 plus integral along c2 plus and so on, integral along cn. Alright, so this is the benefit of Cauchy's theorem, and so many typical questions can be simplified by applying Cauchy theorem. Alright, so next, Cauchy integral formula. So we'll understand these theorem and this with the help of some examples. So let's understand Cauchy integral formula. So suppose we have a simply connected region and that one curve, closed curve is taken as C, and inside this curve a point Z0 is taken, right? Okay, and this Z0 is further encircled with a circle C2. You can see here, yeah, here you can see with the circle C0 it is being encircled, right? So Cauchy integral formula assume that fz is analytic in region R, but if we multiply by this vector 1 by z minus z0, that is analytic except at z0, means at z0 it is not analytic. Note this point and consider the following integral around C. So we can write this I is equal to fz by z minus z0 dz, right? So, using Cauchy's theorem for multiple curves, because this C0 is what? This is inside the closed curve C. Okay, so for multiply connected region, if we use Cauchy theorem, this integral along C will be equal to integral along C0. Right, so C0 is our assumed circle which is being drawn by taking Z0 as center and very small radius. Okay, so here we have shown in the enlarged manner. So C0 is a circle, so we can write its equation as C0 such that mod Z is equal to small r. So if I remove this mod, I will write this as r e raised to the power iota theta. Alright, since this is equation for the center at origin and this is equation for center at z0, right? So this point is z0, already mentioned. So C0 becomes z mod of z minus z0 is equal to small r, right? So we have removed the mod and then we are taking this result. Okay, so on right hand side integral we are going to substitute all these values. So here I have mentioned and substituted all the values. So finally whatever we assume to derive some derivation, to have some results, we have to eliminate it. So for that we have to take small r as 0. So this term cancelled. What we have, 2 pi iota fz0. After integrating, this is also cancelled. Iota we have and theta is integrated, so 2 pi is the result. So this is the result we have obtained here. So this shows that fz0 is equal to 1 upon 2 pi iota close integral over c fz by z minus z0 dz. So this is known as Cauchy integral formula. Alright, so as I want to show you here, so this application for Cauchy theorem for multiply connected regions we have applied here to derive the Cauchy integral formula. Alright, I hope it will be clear. Okay, then we will be using these results by solving our questions. So let's have a summary of Cauchy integral formula. So we were having a closed curve C, and inside this closed curve C, a point Z0 was defined, at which our fz over z minus z0 is undefined at exact z0. So the value of the function at z0 is denoted by this formula. Right, so Cauchy integral formula is what? F is equal to, if z naught becomes a, then f is equal to 1 by 2 pi iota closed integral over c, fz over z minus a dz. Understood? And this formula is very useful. Right. So if z naught is outside C, the integrand is analytic inside C. Right. This is very important point. Since we know that if z is analytic inside C, so if z naught is outside C, then by Cauchy theorem, this must be 0. So these are the standard results which can be used. Z naught is inside C, then we can write as f z naught, and if it is outside C, then the value of integral will be 0. So this is very important point, so you have to remember this. This inside value is fz naught, outside value becomes 0. Alright then. So here in short, I have shown here the summary of both the cases. So the value of integral fz over z minus z naught is 2 pi iota fz naught if it is inside the closed curve C along which the integral is being taken, and it is 0 if z naught is outside C. Let's solve some examples based on this. So here 1 by z square dz, where C is an ellipse center at 2 comma the center. Accordingly we can adjust the center. So here we have to use any one of the theorems. The rational function 1 by z square is analytic everywhere except at z naught. Right, you can notice the point that z square means if we put z is equal to 0 here, means origin it cannot take, means except origin this function is analytic everywhere, means it is integrable except z is equal to 0, and since that point is inside C, z naught is not a point in period or 2. So if we draw this ellipse, we can find that this is analytic everywhere except z is equal to 0, but z naught is not a point in period 2 or on the simple closed elliptical contour C. It is not inside this, because when we draw this, origin will be excluded. So if it is excluded, the value of this integral is 0. Similarly, next question, closed integral over C 6 by z minus 3 dz, where mod of z minus 3 is equal to 5. So this circle is shown here, mod of z minus 3 is equal to 5. So the points which are singularities, rather singularities means z is equal to 0 and z is equal to 3. These are the 2 points at which function is not defined. So we have encircled these 2 points, origin and 3. Right. So the function, given function is analytic everywhere except at 0 and 3. Then we can use the concept of Cauchy theorem for multiply connected region. So closed integral over C is equal to integral over C1 plus integral over C2, which are the two circles enclosing 0 and 3. And then we have easily simplified by breaking into partial fraction. Then we can easily integrate the 4 integrals. 1 upon z, this by breaking it into partial fraction. So this along C1, we can check that this function is analytic inside and on the circle C1, which circle C1 I want to show you, the circle C1 here, which is enclosing the point C. Here no 0 is there, so Cauchy integral formula can be used, and this becomes 2 pi iota, that is 4 iota. So here value is substituted. So let's have consecutive values of I2, I3 and I4. 1 upon z minus 3 is analytic inside and on circle C2. C2 is what? The circle which is enclosing the origin. That's why its value is this. So now we'll check about the curves integrals I2 and I4. So these are 0 because those points origin and 3 are inside the circles. That's why two integrals are 0. So substituting all the values of the integral, we are having this value. Alright, moving ahead, next example, we have this integral z over z square plus 1 and two circles, two path we are given. So first part C2 z plus iota means center is minus iota, and we'll check that which point is inside and which one is outside. So z naught is equal to minus iota. So using Cauchy integral formula, it is inside, so we'll use Cauchy integral formula here. 2 pi f z naught we have already studied, so that is being used here, and the result pi iota we are getting. For next, once again we can use Cauchy integral formula, and using the first part we are having here, the result is 2 pi iota, right? Similarly, we can understand the derivative formulas for Cauchy integral formula. So here we can use partial fraction. So here a small difference delta z is taken from z naught. So some point z naught plus delta z is taken as the neighborhood point. So we can use the first principle of derivative here. So f of z naught plus delta z can be written like this, and then we have subtracted from second to first, and then accordingly the calculation are done here. Then we have the limiting case. If delta z tends to 0, we can notice this, that the derivative of fz naught is what? 1 by 2 pi I closed integral over c fz over z minus z naught whole square dz. Right? So this is the Cauchy integral formula, first derivative. Right? So similarly we can do for nth derivative. This is second derivative. F double dash z naught is equal to 2 by 2 pi iota closed integral over c fz over z minus z naught whole cube dz. And similarly for nth derivative we can write this as nth derivative of fz naught, that is equal to n factorial over 2 pi iota closed integral over c fz over z minus z naught raised to the power n plus 1. Right, so assuming all the conditions for analytic function, we can derive these formulas. Let's have one more example. So evaluate this integral z cube over z minus 1 whole square. This has pole of order 2. As z is equal to 1 whole square is there, and z is equal to 1 is very much inside this. So here we can use the formula, Cauchy integral formula. Gz we can assume as z by z minus 1 whole square, and that is being taken as the derivative here. And since z is equal to 1 is the point of